Good morning, class 10th. Today we are going to discuss another chapter in circles, that is tangents. What are tangents? And there are certain theorems and certain problems based on tangents. Tangents are very useful for constructions also. So we'll discuss all that about. First of all, I've drawn figures here on the board. If you see here, there's a circle with center O and there is a straight line L which is not cutting or touching this circle. Both these are on the same plane. They are on the same plane. The circle and the line are on the same plane. This line L is not cutting the circle. This kind of a situation, the line is called non-intersecting line. It is called a non-intersecting line. In the second case, I have a straight line L which is touching the circle with center O at only one point P. There is only one point P at which this straight line is touching the circle. This kind of a line is called, this kind of a straight line is called tangent. Tangent always touches the circle only at one point. It touches only, it doesn't cut, it touches. In the third figure, I have a circle and a straight line L cutting the circle at, intersecting the circle at 2 points P and Q. This kind of a line, a straight line, is called a secant. So non-intersecting line, a tangent and a secant. Then look at this figure 4. In the fourth figure, I have taken a point P inside the circle. I have taken a point P inside the circle, and from P I try to draw tangent to the circle. You will realize that any line drawn through the point P which is inside the circle will cut the circle, intersect the circle at 2 points. Exactly at 2 points. It will intersect the circle anywhere line you draw through P. If P is inside the circle, it will cut, it will intersect the circle at 2 points. And again we had told you that this, so we cannot draw any tangent to a circle from a point inside the circle. We cannot draw a tangent to a circle from a point P inside the circle. If there is a point P on the circle, somewhere on the circumference of the circle, this point P is on the circumference of the circle, then I can draw one straight line which is called tangent. I can draw one tangent on a point P which is on the circumference of the circle. Now let us see the sixth figure. This is fifth, and let's see the sixth figure. In the sixth figure, I have a point P outside the, this is the point P outside the circle, and I can draw two tangent to the circle. I can draw two straight lines which are tangent to the circle, PA and PB. So from inside the circle, if a point P is inside the circle, I cannot draw any tangent. If the point P is on the circumference of the circle, then only one tangent can be drawn. And if there is a point P outside the circle, then I can draw two tangents to this any circle, and PA and PB will be always of equal length. PA and PB will be always of equal length. Now let us discuss the theorem about tangent. The statement of the theorem is a line drawn through the end of a radius and perpendicular to it is a tangent. Like this is a circle drawn here. This is a circle drawn here. And OP is, P is any point, O is joined to P. P is on the circumference of the circle, and a line is drawn perpendicular to it. A line is drawn perpendicular to it. We will have to prove that this line is tangent to the circle. This line is tangent to the circle. a circle with center O, OP is radius, and L is a line through P perpendicular to OP. Now, what we require to prove is that line L is a tangent. Line L is a tangent to the circle at point P. When I'm showing it like this, extended to infinity. When we talk of a line, it has indefinite length. Now, if what I've done is, I have taken any point Q on the line L, which is not at P, leaving P except P, you can pick up any point. And this point Q, you will realize, will be somewhere outside the circle, because only point P is on the circle. If you realize this, that this point P is only on the circle where this line is touching. If I take any point anywhere else on this line L, it will be outside the circle. It can't be on the circle. So this point Q is taken somewhere on the line L, and I have joined O to Q. I have joined O to Q. It could be taken anywhere, on this side, or this side. We have joined O to Q. Now please just look that OP will be equal to OR. They are the radius of the circle. You know what the radius is. Any point joining the center of the circle to any point on the circumference of a circle, a line segment joining center of the circle to any point on the circumference of the circle is radius. So OP is radius, OQ is radius. We define the locus. We define the locus of definition of the circle with the basis of this only, that this is P and R are moving point which move in such a way so that they always remain at a fixed distance from O, center of the circle, and the path traced is called the circle. So we said Q is a point which we have taken anywhere on the line, but this point Q is not on the circle, it is somewhere outside, and we have joined O to Q. We are saying OP and OR are equal because they are the radius. So the length OQ will be OR plus RQ. It will be sum of two segments, OR and RQ. OR plus RQ. But we know that OP and OR are equal. We know OP is equal to OR. So what we are doing is, instead of OR, I am putting it equal to OP. So OQ will become OP plus RQ, or we will say OQ is greater than OP. Obviously, OQ is greater than OP because OQ is greater than OR. OQ is greater than OR. So OQ will also be greater than OP because OP and OR are equal. So OQ is greater than OP, or in other words, we can say in the reverse fashion that OP will be less than OQ. OP will be less than OQ. That means I told you that Q can be taken anywhere on the straight line except at P, because P is the point which is on the circumference of the circle. This point Q is anywhere on the line except at point P. That means the position of Q is not unique. Can be here, can be here, can be here, can be anywhere on the line. And we will realize that OQ will be greater than OP, or any number of lines which we draw from the center of the circle to any point on L will be the length OP will be the shortest distance amongst all the lines which we can draw from O to line L, because P is also lying on the line L. P is also lying on the line L, but the only unique situation of P is that it is lying on L as well as it is lying on the circumference of the circle. But the Q can lie anywhere on the line L, but not at this point. There cannot be 2 points lying at the same point. So Q can be anywhere else, and we have proved that OP is the shortest distance among all these lines. And you know shortest distance is always they're perpendicular. So this line L will be tangent to the circle at point P. The point, we can take Q anywhere on the line L except at P, and we will find OP is the shortest distance. So line L will be tangent to the circle at point P. This is the converse of the first theorem which we did just now. Here it says the tangent at any point of a circle and the radius through that point. This line L is the tangent at any point P, and PO is the radius through that point. So it says that both OP will be perpendicular to the tangent. The line, this radius will be perpendicular to the tangent. It is very important property. We will be using it in construction all the time. It says the tangent at any point of a circle, the tangent, we have taken L as tangent at any point P of the circle, and the radius through that point, and the radius through that point, PO is the radius through that point, are perpendicular to each other. They are perpendicular. That means we have to prove this line OP is perpendicular to the tangent. A circle with center O is given and tangent L at a point P on the circle is given. We have to prove OP is perpendicular to L. It's very simple. We are going to follow the same process. We'll take any point Q anywhere on the line L. We are saying this is the tangent. We are saying it is tangent. Take a point Q anywhere on this line L except at P. We are not talking of the P. Q could be taken anywhere on the line except on P, because P is a single point. P is a single point because the tangent touches the circle at one point only. So we cannot take other points at P. Only P is there. So Q can be anywhere on this line, and I join O to Q. If I join O to Q, then OQ will be equal to OR plus RQ. OQ consists of two segments, two parts. One part is OR, the other part is RQ. OQ is equal to OR plus RQ. Next is OR is equal to OP. OR is equal to OP. Why OR and OP are equal? Because OR and OP are radii of the circle. So both radii will be same. So I can replace OR with OP, and OQ becomes equal to OP plus RQ. That means OQ is greater than OP, because when we are adding something to OP, we are getting OQ. So OQ is greater than OP. OQ is greater than OP, or in other words, I can say OP is less than OQ. OP is less than OQ. And we told you the position of Q is not unique. The position of Q is not unique. Q can be anywhere on the line. That means any point I take on the line L and join it to O, I'll find the distance of that point Q, which is not unique, will be greater than OP. That means if I draw many line segment starting from O and finishing it on the line L, I'll find OP will be the shortest distance. OP will be the shortest distance according to this, and the shortest distance between a point and a line is perpendicular. Perpendicular distance is the shortest distance. That is why OP will be perpendicular to this line L. So the radius is always perpendicular to the tangent at the point of contact. P is the point of contact. O is the center of the circle. If I join O to P, then OP will be the shortest distance of all the distances which can be from O to line L, like I have illustrated with the point Q, and as I said, Q is not a unique point. Okay, we have the next theorem and series of tangents where it says if two tangents are drawn from an external point to a circle, P is an external point. We have drawn two tangents, PA and PB. If two tangents are drawn from an external point I have a point P, external means outside the circle. From P I have drawn two tangents, PA and PB. As you know, we had already discussed, if a point P is outside the circle, then it is possible to draw two tangents to the circle. PA and PB are two tangents drawn. We have to prove then, number one, the length of tangents are equal. This is also an important property which we will be using many a times. The length of the tangents are equal, that means PA is equal to PB. The tangents subtend equal angle at the center. The tangents subtend equal angle at the center means angle POA is equal to angle POB. Number 3, it says the tangents are equally inclined to the line joining the point and the center of the circle. That means tangents are equally inclined to the line OP. That means angle APO will be equal to angle OPP. That is what it is. Given is P is an external point, PA and PB are tangents drawn to a circle with center O, which I have already discussed. What is required to prove? PA is equal to PB, which I have also told. We have to prove angle AOP is equal to angle BOP. That angle subtended by the tangents at the center are equal. And angle OPA is equal to angle OPB. That means the tangents are equally inclined to the line joining the point P to the center of the circle. For proving, what we will do is we will take the triangle OPA and triangle OPB. We will take the triangle OPA and OPB and we will prove the triangles to be congruent. We will prove them to be congruent. This OPA and OPB will be proved to be a congruent triangle. How are we going to do it? You can see OA is equal to OB. Radii of the same circle, OA and OB are radii of the same circle. They are going to be equal. OP is a common line between the two, common line segment between the two triangles. OP is the part of triangle OPA also. OP is also part of OPB. So OP is common to both the triangles. And the angle PAO or OAP is equal to angle OPB 90 degree because radius and tangent are always perpendicular. We have already proved that radius and tangent are perpendicular to each other. So when we have proved two sides, actually in these two right angle triangles, these are two right angle triangles. This angle is right angle, this angle is right angle. So in these two right angle triangles, we have proved their hypotenuses are equal. Which are the hypotenuses? OP is the hypotenuse. So for both triangles, hypotenuse is equal and one of the remaining side, which is the remaining side? OA is equal to OB, radii of the same circle. So these two triangles are going to be equal to each other in each and every respect by the property right angle hypotenuse side, RHS, property of congruency. Now when these two triangles are equal to each other in each and every respect, then we will say PA is equal to PB, CPCT. Two sides are equal, third side remains, so third side will be equal. PA is equal to PB, CPCT. That is the first point we had to prove. PA is equal to PB. Now I will say that angle AOP is equal to angle BOP. Angle AOP is equal to angle BOP. Again CPCT, congruent part or corresponding part of the congruent triangles. And then APO will be equal to BPO. Will be BPO, yes, CPCT. So we have proved all 3 points what we require to prove. This is a very important theorem and we are going to use it time and again in different problems.